Okay, so I didn't know who was going to be here and who was going to be online. And so I thought, hmm, maybe I'll just have a very small slide presentation. And then basically I'll be like one of those singers who takes requests. So I made a website that the URL for it is right here. And normally I put like a QR code, you could scan it with your phone, it would open, but we don't do that in Green Bank. So write that down, and Jill will email it to you, I think, later. And you'll see that website in a few minutes. But what I did is I basically said, what are the most fun projects that have also led to scientific discoveries or innovations in education or communication that have happened in the last several years? Let's just put them all on a website so I can play with them and show people what's going on and see what people are interested in. So yes, and one of them, the background picture here at the end, we will play with Worldwide Telescope, and we will let Will drive around on Mars with the Xbox controller. And we also have this thing, which features, this is called an augmented reality target cube, and we recently published the first augmented reality enhanced paper in the Astrophysical Journal, and so I'll show you a little bit of that too. That one needs a live internet connection on your phone to work. So we'll let people, again, everything afterwards, hopefully just come around here. I'm sorry for those of you who are online, wherever I'm looking at, you can buy one of these from Amazon and try it at home. So this is the website, and don't worry, you're not supposed to read this here, but all of these things on the real website are live, and so they're a vast assortment of visualization things and science education things and actual science things and even a COVID thing just for fun. And so I'll show you that in a few minutes. But you're probably wondering, a little bit beyond the story that Jim told you, like, how did this happen? How did I wind up in this kind of weird hybrid, and I don't mean Zoom, world, somewhere between science and technology? And the answer is that my interest, and I didn't put art on here, so when I was a kid, I was really interested in art, and I wasn't a great artist, but I was a little bit of an artist. And I was interested in science, I was interested in history, I was interested in everything, okay? But today, we're mostly going to talk about science and technology, maybe with a little bit of art thrown in, okay? But then, people in academia, they mostly think about research or teaching, right? So there's like these three axes of research and education and communication. And I also don't really feel only passionate about one of them. I actually think that being able to kind of go back and forth from one to the next and kind of like wander around, both in kind of like how you think about things, but also how you work, is really fun. And so if there's one point that I want to make tonight, it's that this all leads to, great advances for humankind and whatever, but it's really fun. And so, my goal is really to let you guys have some fun tonight. And so you're all familiar with the image on the left in terms of a good example of science, but then the image that you see on the right is a video of what happens after you scan a QR code that's printed in a paper, and then the data are loaded onto your iPhone, and you look at your iPhone, you look at your hand holding this cube on the screen of the iPhone, and you move this around. And so, in case there are aficionados here, those are the Perseus and Taurus molecular clouds, which appear to touch on the sky. And that is a 3D dust map that actually shows you those clouds in real 3 dimensions and shows you that very clearly when you use these 3D visualization techniques. They do not touch on the sky, and in fact, they're on the surface of a big supernova remnant, which is fascinating. Okay, so this is my equation for tonight, with set theory involved as well. So science plus technology is the set of fun and discovery. Okay, and so that's the plan here, and I will wander around just like that, not on exactly that path for those of you who are very serious. But you heard Jim say that I have been here several times, and I have. And the first time that I was here, I was coming here with my advisor, who in graduate school, my main advisor was Phil Myers, who's a bit older than me, but not like a huge amount older than me. But he was not as interested in technology as I was. And my computer that I had ordered, my laptop computer in 1986, had not yet arrived by the time I left, because of course I was the graduate student, he was the advisor, so I was coming here for like a week or two, and he was coming for 2 days. So anyway, so I said, oh, Phil, that's okay, I got a bag, and you can put this laptop in the bag. And so he always harkens back to this infamous red bag, which contained my first high-tech device. So that is actually a Zenith Z180 computer, which was extremely sophisticated at the time. And in particular, this thing here, this was a floppy drive, or 3.5-inch floppy, and this was a hard drive. I will let you guess. Who wants to guess the capacity of the hard drive in 1986 or 87? I can't remember what year it was.
256K.
10 megabytes.
Oh my God.
10 megabytes. This was expensive.
Top of the line.
This was the best. And so here I was at Green Bank. I just thought I should tell one Green Bank story, and then we'll move on. So Phil brings this bag to Green Bank, and I set up this computer, and I'm like all ready to, analyze my data, which of course I had to basically put on a floppy drive, but whatever. Well, because you wouldn't want to use Wi-Fi, which didn't exist in 1987. But anyway, yeah, and then there I was all ready to do this, and then the tape drive at the 140-foot broke, and Tom Troland, who some of you know, had to take me to not this building, but the one, the lab next door, and teach me how to use a card punch. So thank you, Green Bank. I got to go back in time and learn how to use a card punch when I brought this, okay? So, but this is kind of a metaphor for my whole life, okay? Where I'm always trying to live like a little bit in the future, not a distant future, but like the possible future. And then people are all like, what are you doing that for? Okay? Anyway, so yeah, we also did this stuff that Jim mentioned, which is detecting a bunch of magnetic fields, but that's not what today's talk is about, but I just thought you would like to see that it says the Green Bank 43-meter telescope right there on that paper. Okay, so there's young Dr. Maddelena, although not as young as when I knew him. That was the picture I could find Ron easily, so anyway, where is he? Wait, I saw him. Where'd he go? Oh, there he is. He's right behind. Sorry, you were blocked. Yes, and that is the extremely famous map of the Orion molecular clouds that Ron made. And I wish I had scanned this in advance, but in Ron's thesis here is the polarization map that I made with him when I was 21 years old by scouring the literature for measurements of background starlight polarization and using very sophisticated plotting software that Ron wrote. Anyway, but he got me started, and I'm very grateful to you, Ron, forever, in caring about molecular clouds and even about magnetic fields, which I actually wound up working on for my thesis. And so just for fun, Ron, I wanted to show you that, that this is the Planck polarization map in the background here, and this is from a paper that Mike Foley, who's a graduate student at Harvard now, is working on. And this is just one of many, many figures that does exactly what Jim was talking about, which is overlay many different wavelengths. And you can actually, I didn't bring the polarization vectors from the thesis, but they actually show, I don't have oh, here's a pointer. So this is Barnard's loop, for those of you who know. This is a loop of H-alpha emission ionized gas. And you can see the magnetic field kind of wrapping around it. And you can also see that it has something to do with this other ionized gas. And anyway, you can read the paper, okay? But what I really wanted to show Ron is that now, instead of what you saw here, that this says 3D asterisk up at the top, because again, for the spectral line radio astronomers here, that means position, velocity space. And like, we used to think we were so cool, because at least we had a third dimension, and most other areas of astronomy did not. But it's a fake third dimension unless you do cosmology and you can, have a Hubble law and velocity is real distance. But now, what I've been working on for the last several years in collaboration with Doug Finkbeiner and Joao Alves and Catherine Zucker, who's the leader of so many of these papers, is real 3D maps. And so like, this is something I never ever thought I would see in my lifetime. So I have to show you. Okay, so this is one of many examples I could show you, and I'll show you some more later. But Ron, just for you, so here's one of your clouds in 2D. This is a high resolution 2D dust map. And this is Orion in actual 3 dimensions okay? And again, I'm not giving a science talk tonight, but if you want to know how 3D dust mapping works, anybody, you can ask me later, and I'll tell you. But like, I literally never thought that I would be able to turn around molecular clouds that are many hundreds of parsecs away. And these maps, by the way, have 1 parsec resolution. So it's crazy. And I'll show you some of the fun things that we've done with those since then. But I wanted to mention that I'm also grateful to the summer program I was in 1983, because the mini classes that were at the beginning of it, most of the people there were not interested in astronomy, they were interested in earth science. And the prominent earth scientist who taught the classes was James Hansen. And some of you probably know who that is. That's the person who sounded the alarm about climate change in the first place. He was a professor at Columbia, and he worked at GISS, the Goddard Institute for Space Science. And this is the paper here, which has like 1 million citations. You know, and it very moderately says, you know, what's the climate impact of increasing atmospheric carbon dioxide? And there's one of the figures on the right, and we all know the news is absolutely terrible and getting worse. But at that point, these papers, and this is going to come into this later, this isn't just stories about 1983, I promise, had a huge amount of uncertainty. The computer simulations that went into doing this had a lot of uncertainty, some from not enough data to constrain the inputs, some from the fact that the computers were not what the computers are today, and so you had to make a lot of approximations and then not run the calculations for very long, you know, and then maybe some of the atmospheric chemistry wasn't perfect. And so the papers were published that said, well, these bad things are likely to happen, but we're a little bit, you know, uncertain about it, so, you know, maybe it'll get better. I'm exaggerating, I'm making it simpler than it was, but that's sort of how people thought about it. And then what happened was George W. Bush in the early 2000s, that would have been, right, was referring back to these papers from the early 1980s, from 20 years before, saying we don't have to worry about climate change because it's very uncertain. And at that point, I had this other crusade in my life in the back of my mind to go back to what I had learned ages ago in a field that I didn't then work in, but teach people to understand uncertainty, okay? That uncertainty means certainty. It means, you know, how certain are you about something? And it means that we can quantify this. And so there's this whole project now that I and 40 other faculty at Harvard work on that's called Prediction X, or the Prediction Project. And so I'm the host of this project. And what it does, some people call it uncertainty. That's not the name of the project, okay? But the idea is to say that computer simulations of climate, of finance, and of health are the modern way that we foretell our future. And they came from the Oracle of Delphi and ancient Mesopotamian sheep entrails and things like that. And so the online course, it's not really a course, but the online thing that we made that has interviews with mostly people at Harvard, but faculty all over the world, experts in Mesopotamian sheep entrails and, you know, Indian mathematics and things like that, is supposed to build people up to appreciating that modern simulation, computer simulation, is different in that we test how well things work, and we go back and we iterate and we change the models and we make them better, and that uncertainty is the quantification of how well these models do. Well, I'll just tell you the disappointing news is that 200,000 people or something have taken this course online, hundreds of Harvard undergraduates, because there's now a Harvard course that goes with this, have taken this. And it turns out those are the choir. So you're like preaching to the choir, and they get a little bit better at their appreciation, including the 100,000 people online, okay? And it's really hard to explain uncertainty to people. So I've had a lot of fun doing this project, and I thank Jim Hansen for it, and this little logo at the bottom, I'll show you on the website in a minute, is a new initiative with a new friend and collaborator at Google whose name is Guha, who runs something called datacommons.org, which is an amazing collection of data that Google uses to help you with a lot of things that you don't even know about. But anyway, they're trying to assemble a lot of data that's relevant to anything having to do with climate change and climate mitigation, and then make that data useful to researchers. And so Harvard is a partner in this effort now, and so that's my contribution at the moment. But this prediction project is still ongoing. And so before I show you the website, I just want to say that there's a program at Harvard that we started called Seamless Astronomy, where the goal is to integrate lots of different software projects together so that people can do amazing things without realizing that they're doing amazing things. Like, they don't have to worry about how all this software magically talks to itself. Not itself, but each other. And originally I used to use travel sites as an example of how this works in everyday life. But I was on the plane on the way here, on this little dinky plane, okay, this Delta tiny plane. And they were, of course, offering me, I'm sorry, I wasn't in Wi-Fi, right? And so I'm on the plane, and I just took a screenshot of this webpage as a perfect example of how we live everyday life with this kind of integration of technology that we don't notice, okay, but that is incredibly complicated and relies on a lot of cooperation amongst people and organizations and software projects, and somehow works. So if you look at this, right, this is Delta Airlines partnering with GoGo, which is a company that gives you internet access, and then I could pay for this with PayPal or my Amazon account. Now you realize, of course, that Amazon's going to harvest that I was on this plane, and then they're going to like offer me a new suitcase or something like that. So it's not like this is completely innocent, all of this, okay, this cooperation. But it shouldn't be innocent for scientists either. You know, they should have all kinds of motives to do this, right? And then, you know, I can pay 4 different ways, so that's 4 different credit card companies if I don't want PayPal or Amazon, who, by the way, already have my credit card information, but never mind. And then I didn't fill this in on the screenshot, but you realize I could use any of these password management programs, including Google itself, that somehow, even though I tell it not to save my passwords, miraculously has all my passwords, okay? So why, then, isn't, like, education like this, okay? Science is sometimes like this, but what bothers me is that education is not at all like this. So some kid goes on a flight and, you know, asks their parents for Wi-Fi, and sitting next to them is their parent who opens this, and then meanwhile they go to school and they don't even know what a computer simulation is, even if they've gone to a really, really fine high school, never mind knowing how all this software talks to itself, and I keep saying itself, each other, whatever. And the kind of technology that people use in gaming, okay, they don't use usually in education, and a lot of us don't even use it in research. And so hopefully what I'll show you in a few minutes looks like something you'll want to use, like one thing I'll show you out of a dozen or something. Looks like something you want to use. And so just for fun, I also, Wednesday, which was the day before I was getting ready to leave, I just took a bunch of screenshots as my day was going on to show you kind of like, where does this actually play into my real world. And so, you know, this is a screenshot from an ALMA proposal. ALMA, for those of you who are not astronomers, who's anybody here, is the Atacama Large Millimeter Array. So it's a big radio interferometer, and there was this big telescope proposal for hundreds of hours. And so we were working very hard on this particular figure, which does this thing that Jim was talking about, integrating across wavelengths and observatories. And we were focused really carefully on, like, believe it or not, what color to use for the so-called CO emission in each one of these panels, and you'll notice that it's purple in every one. And this is because in cognitive science, there are a lot of subtle effects, like people seeing the same color and thinking it means the same thing, that a lot of astronomers and teachers and educators and textbook writers, they don't pay attention. And they think like, well, that's not important. Well, it turns out if you change the colors in this figure, it doesn't make any sense. And so this was us changing it so that it does make sense. You know, and then like in another meeting, I was talking about a project that we have that is going to recognize images in all journal articles. And so then you can put the images back on the sky where they go in this Worldwide Telescope program that I'll show you. And you can also harvest all the metadata about what's in the figure captions, and it describes the image, and then people can search for the images. And so this is a partnership with Jill Nyman, who's an information science professor now in Illinois. But this is the kind of stuff that goes on behind the scenes, and suddenly you're going to be able to go to ADS, which, by the way, most people don't know this. So ADS is, again, for the non-astronomers, the service that gives you access to journal articles. And already, right now, the newer journal articles, you can see the figures, just the images from the paper separately in this thing called Astronomy Image Explorer, that most people don't know exists, okay? But you can, and so you can search by images if you're looking for. And what this will let you do is make that search much better, but also be able to like just click on the image and see where it goes on the sky. And I didn't put that in the slideshow, but I'll show you how to do that in a second. And then this is just a screenshot from actually this Orion project, Ron, of this glue software that we seem to use to do everything. these days. And the bottom right is a screenshot from a meeting about something called cosmic data stories that I'll talk about in a minute, where we got a few $1 million from NASA to use modern technology to explain and teach data science to high school students and community college students by taking famous discoveries in astronomy, some very old, like Hubble's law that's in this picture here, and some very new, and give the students enough real data and real software and guidance that they can reproduce those discoveries, but not just reproduce them, but then play with the same data and learn whatever they want. And so this is like how I get to live, okay? But most people don't, and not you, maybe many of you do, okay? But people who are in school and who think that science is, you know, dry and boring, it's because they don't get to have some program like what you see here, which is just a screenshot of Worldwide Telescope doing one of the million things that it can do, you know, showing you things moving and within the solar system, and then zooming out of the solar system. And, you know, I can use this same software to show you the solar system, the surface of Earth, panoramas on Mars, imaging at any wavelengths that you want, 3-dimensional views, 2-dimensional views, and it's all free, and most teachers don't even know that it exists. And so, you know, that's disappointing sometimes. So let me go here, and we'll open up this web page. I keep trying to get rid of these controls, and they keep coming back. Oh, there's zombie controls. Okay, so here's this web page, and I'm just gonna like very quickly tell you what each thing is, and then I'm gonna just ask people to sort of shout out what you would like to hear more about, or raise your hand and ask. Okay, so this is, we used data from Gaia to do these 3D dust maps, and we figured out that we don't understand the structure of the galaxy, and that there's this giant thing called the Radcliffe wave, which is the spine of the local arm of the galaxy. This is our latest fun, where we learned that all major star-forming regions near the sun are on the surface of a gigantic empty bubble. This is that prediction project I was telling you about, which also spawned this path to Newton that you'll see in a minute. This one is the data and climate project that I told you a little bit about. These two I definitely want to show you, so I will in a minute. But this shows you that it's not all about high technology visualization, and I put dimensions of discovery, because a lot of what I like to play with, let's say have fun with, is thinking about, you know, like if you're looking at 3-dimensional data, could you use a 3-dimensional thing? Okay? Or if you have a really big table with a lot of columns, how many dimensions or columns of that table can you encode effectively in a graphic at once? And so dimension doesn't always mean like this is a 3-dimensional cube. But here on the left, that is a model of Orion again. Ron, see, I made this Orion themed for you. Okay, that's a model of Orion that was made by a group of the world's experts about Orion, using craft supplies to try to understand the 3-dimensional structure of Orion. And it's a fun video. I'll show it to you if you want. And then this one explains how the augmented reality technology works. This I already showed you. This is Orion in 3D. Again, I can talk about how we did that. This is Worldwide Telescope, which we will definitely play with at the end. This tells you something about this GLUE linked view visualization software that I keep saying is so important to all the discoveries, so maybe I should show you something about that. This is this object I decided to feature over here and leave at Green Bank, a couple copies with you, and it's called the Path to Newton. And so in the middle of the prediction project, so let me just show you a little bit of the prediction project so that you can know what I'm talking about. So the project itself has a layout like this, where some of it is sort of pedagogical stuff that is itself interesting, but then it goes in sort of almost chronological order, where the older stuff is, some of which still goes on, which is why I say almost chronological, like astrology, for example, okay? But it's omens, oracles, and prophecies, it's called. And you can just read for yourself what's in there, all kinds of interesting practices. And then in the middle, we talk about how the modern system of what we call science, which includes modern prediction, kind of had to be invented. And so we call that part of the project the rise of theory. And part of that is this thing here called the path to Newton. And what the path to Newton does, I'll just open it full screen here. Is it says, if I'm Isaac Newton, and I'm going to put the text away for just a minute. It says, if I'm Isaac Newton, okay, and I'm all the way over here, what is it that I needed to know in order to make a predictive theory of gravity? Okay, so this is a way to teach science through history, or teach people who are interested in history about science. And by the way, the original version of this I made for myself when we were trying to develop this part of the course, because I could not keep all the names and dates and things straight in my head. And so I was just making this kind of chart. And then when it was the last time I was on sabbatical. I was on sabbatical in 2017, and I was doing this for fun. And when I got back to my colleagues, and they were like, why don't you turn that into a real thing? I thought, oh, okay. And so we did. And what happens is anything that's green here, I'm sorry for anybody who's colorblind, but this is green. And then if we go way back in time, a lot of these things are gold or yellow, okay? So stuff that's gold is basically wrong, and stuff that's green is right, okay? So if the idea was correct, it gets a green circle. If it's sort of correct, it gets partial credit, and if it's wrong, it's wrong, okay? But what this does is it shows you all the way from the ancient Babylonians through many other cultures, what was it that sort of fed into Newton or confused people along the way. And so you saw you probably didn't see what I just did, but I clicked on one of these circles. So say I'm interested in Ptolemy, I can click on Ptolemy, and then it'll go here in the story to tell me about Ptolemy. And I could just be reading along, and this is in chronological order over here, and I'm like, oh, who's John Philoponus, and what is this about celestial and terrestrial motion? So I can click there, and it'll take me to that place. So the poster does not do that. Okay, but it's supposed to be kind of inspirational for students in classrooms in particular, or in museums, put it on the wall and then get them to go use this. And if you look up here, you actually see that we also included like what kind of tools were necessary and what kind of math was necessary. And you can see that those lines get more and more populated as you move across the screen, and they end with Newton basically inventing calculus in order to do what he needed to do. And yes, there are telescopes. Galileo, sorry, not a radio telescope, but he gets credit for pointing a telescope at the sky. But so anyway, that's the kind of tremendous fun that we like to have. And so the Path to Newton is part of that prediction project. And then down here, this is the data story. And then these three things are all examples of how we try to explain uncertainty, one of which involves COVID data. And then these are things that we just offer to people to try to help people make better visualizations. This is a relatively new project where we're trying to make a metadata standard for timeline. And this is a software company that we don't have to talk about tonight, but that was built off of our academic work because people were interested in other fields. And so we're like using the same software that we used for the local bubble to see DNA in 3 dimensions curled up inside of the nucleus of cells and things like that. So, okay, so now I'm going to stop for a minute and just say, what questions do you have? Which of these things are you most interested in? Because these are all live links to videos and demos, and I can do whatever you like. And I just thought, why don't we tailor this to the audience? So somebody please make a request. And I don't sing or dance, so you cannot request actual song. Absolutely, absolutely, yes. So the augmented reality one or the craft project or both? The left one. Okay. Sure. With narration? Yeah, sure. Some of you know these people. I think the sound will play over Zoom. I'm not sure. You see, I have to turn the sound on my computer in order to do this. What's going to happen?
I don't know. We'll find out.
Okay.
Brave new world.
Orion that we built here in Joao Alves' office at the Orion Unplugged meeting in July of 2015 in Vienna. We have 2 Orion experts, Joao
and John Bally over here, who are going to give us a tour of the major features of Orion. So, Joelle, maybe you could start by showing us the stars that we're familiar with so we can orient ourselves from the front view. Can you
Sure.
point?
So the stars are the fluffy balls, the blue ones, and if you align,
I got it.
you got it. So then you have your Orion constellation right there, and then the three
Perfect.
sisters in the middle.
Got it.
That is the supergiants in Orion that you can recognize
Perfect.
naked eye.
And they're not all at the same distance, right? So if I go over here,
Right.
we can see that some of them are very much in the foreground and some very much in the background. And we should mention that this model is only relatively to scale, not actually to scale. Okay, so John, can you tell us about the big shells and the molecular clouds and all
Right,
that?
so the red feature here is Barnard's loop, which is an H-alpha structure which traces apparently a relatively young 300,000-year-old supernova remnant.
Uh-huh.
It's inside the Orion superbubble. In the background there's the Orion A molecular cloud, a 50,000 solar mass cloud, which spawned the Orion Nebula in recent times, namely last million years. The Orion Nebula is the little sphere, and the integral shaped filament is the green structure going into the red structure. The colors here are meant to show the relative Doppler velocity. The southern part is blue shifted compared to the northern part. Just above the integral shaped filament, we have the NGC 1977 region, and then the supergiant in the middle of the 1b subgroup. And what we've learned at this meeting from Eddie Shafley is that there is a giant ring of dust shown in the ground here, of which the Orion A cloud and the Orion B cloud in the north, northwest of Orion, are apparently the most massive parts of a dust ring.
Perfect. And what are these red and blue things that we see throughout the cloud?
So we know that the Orion A and B clouds are chock full of bipolar outflows, and this shows what I think is the largest outflow known to date, which terminates in the
Crocheted by
HH131
Amy's
shock,
Maybe now
about
we
2 degrees south of the Lin 1641 North Star Cluster, which we think is the source of this outflow. And the redshifted flow disappears behind the cloud, although we see optical shocks when we're looking off the cloud edges. Actually, this lobe is fairly close to Orion Nebula, so it's not quite
We
the
don't have
scale.
it quite right, almost. So
But,
this little sphere here is the
Yeah,
Orion
some of those
Nebula.
shocks are just
Yeah.
outside the ionization front of the Orion Nebula.
Perfect. And Joelle, what are these little bead-like things on the filaments and buried that we can't even see inside the cloud?
I think this is the integral shaped filament,
Uh-huh.
and it's bursting with stars.
Protostars. Those are all
Protostars
protostars, and
and
they're
I'm just gonna talk
also
over
the
them for a
red
minute just to
represent
say,
that actually they're somewhat embedded.
this was
Right.
5
Yes, they
days
know.
of work
So one thing that
by like
is
20
not in this
people, and
model
we
yet
kept walking
Ooh,
in and out of Joao's
is
office,
the
arguing about where stuff should
what we see
go,
here is
because
the
we don't
foreground
really know.
population
And this was before
stars.
of stars
the
that
good
would
3D
be
dust mapping
between
that I can show you
the
more of in
ages
a
of
minute. So there was a lot
right
more kind
there
of inference of
and
where
up
things
to
were than they're
somewhere right.
today. Some of what we're
Bellatrix
saying
here.
in this,
So
by the way, is wrong.
There's an older
But
population,
that's
10
important,
million
right?
years,
And
somewhere
if you
here,
think about trying to
and
build
perhaps
interactive
some of us think there's
20
a gradient,
using
almost
software
along the line of
in
sight.
4 or 5 days,
although this is completely new
then
from this
anyway,
meeting.
and probably
was
still
discussed
now, that's
heavily
important.
that we have some
And
kind
so
of
I thought if we did
train
this
of
kind
blue
of
stars
craft
coming from
slicing,
this
and I got
region
this
where
idea
the
from
supergiants are
and a
just
colleague of
the
mine, Felice
oldest one.
Franco,
Got
who runs
and
these
all the others
wonderful
are in
meetings
between.
called Imaging.
Now this is
So there
speculation
we
at the
go. Let
moment.
me take the picture from over here. So show me again where they would go.
They would go
I
somewhere
thought people were
from-
gonna laugh at me,
So this is the
you know,
belt,
for doing this,
right,
but
so
people got super
go.
into it and, you
From
know, really.
here to
learned
the most recent generation of stars,
Orion.
down.
And right, and
across
so I was like
from
explaining that we're gonna
somewhere
learn
like here.
everything from Gaia, and he's talking
The
about
old
how the
generation.
stars are moving,
Now,
and I'm just gonna
This
stop
is
this.
again
'cause-
speculation.
Oh, I guess it
Yes.
has 10
In
more
a
seconds.
year or two with Gaia data, this will be confirmed or not.
Perfect. And what's that shiny stuff in the background supposed to represent?
Well, that's a cosmic microwave background and all.
Of course
the
it
background.
is.
Got it.
I knew that happened, so I was like, okay, I can't stop it now. But,
Perfect. So this
so,
is clearly looking from the front.
stop, guys.
And it's
Okay, so I think what I should do next is contrast that with a video that I think we put on this website. Yes, here it is. So I'm not going to ask how many people saw this back in January when it came out, so I'll just pretend some of you did, and I'm going to bore you, but that's okay. Hang on, hide. You see this every time you hit escape, Zoom thinks that you want to have the meeting controls back, which I most certainly do not. So this was, This is one of my pandemic projects with my friends, mostly Catherine Zucker, whose voice you'll hear in this video. By the way, some mean person on YouTube where this video has like a bazillion views said, did we get a teenage valley girl to narrate the video? No, it's like the genius scientist who did this result. They insulted her voice. But anyway, that is her, and I will let the video speak for itself. But what I want you to look at, not just the science, but I will tell you how many different software packages and how many different people and how many weeks, months were involved in making this very, very short, 1 minute and 13 seconds video. And just compare that to like people using craft supplies in your head. So here you go.
Where did we come from? Not humans, but the sun and nearby stars. How did our galactic neighborhood come to look the way it does? New research reveals that 14 million years ago, powerful supernovas started exploding, blowing out a bubble of hot gas called the local bubble. As millennia passed, the bubble expanded, sweeping up clouds of interstellar gas and dust on its surface. Over time, these clouds collapsed to form thousands of new stars. Our sun was far away when the bubble first started forming. But about 5 million years ago, the sun's path through the galaxy took it into the bubble. Looking out from inside the 1,000 light-year wide bubble today, we see star formation all around us. Stars are forming on the bubble's surface, but amazingly, not inside it. This discovery supports a 50-year-old theory that supernova bubbles from dying stars can sweep up gas that gives birth to new stars, and leads astronomers to wonder how bubbly the rest of the galaxy may be.
Right, so, you like that? Okay. So yeah, that's a short video. We made a whole bunch of longer ones, but let me show you instead. This is the figure that's actually, this paper appeared in Nature in January, and in the paper is this figure, and this is the real data, okay? And here, and by the way, this thing is the Radcliffe wave, and this is another structure, but let me just turn off a bunch of stuff here. Let me turn off the labels too. Okay, and this green thing, by the way, is the sphere that you saw in augmented reality on here. It's much smaller than the so-called local bubble. And so what we were astonished to learn, okay, is that if you, and these skeletons are a way to mark where the densest parts of molecular clouds are, so I'm just going to actually turn off the full messy data. And you can see that those skeleton things, I'll even turn off the motion of the star clusters, they all lie like right on the surface of this bubble. And even for those of you who are aficionados of these things, oops, sorry, this red thing is the Taurus molecular cloud, which is smushed between two of these bubbles. And its structure and its velocity now makes sense because we understand how this all fits together in 3D. By the way, Ron, just for you, here's Orion, okay, over here, in the Radcliffe wave, okay? And let me also show you that it's even better, like, but wait, there's more, as they say. So if I look at the second figure in that paper, you can see the same bubble again, but now I can slide this through time. Okay, so if I go over here and I go back 16 million years, Catherine used, again, a sort of simulation model to figure out what the expansion of the supernova would look like coming from the progenitor stars that we are pretty sure were responsible. And you see, and here you can like turn this around and you can actually see that the clusters, which are shown by the little dots and the trails behind them, is where they came from. And as they get more opaque, that means they've already formed, okay? But you can see them on the surface of the sphere as it expands. And here's the sun, meanwhile, entering this bubble at the same time. And then eventually you get to the current state of affairs, and you can see the origin of these things is somewhere in the middle of this shell. And so basically, yeah, it turned out that, you know, Chris McKee and Jerry Oestreicher and these people who said that these things were supposed to happen, you know, in the 1970s were correct. But suddenly we can use incredibly complicated data science techniques to get these 3D dust maps, and then pretty fun visualization techniques to explain this to people. And if I was going to give you a different talk, I gave a talk a few years ago called from exploration to explanation and back. And so another way to look at all of this work is, a lot of people think that when you make kind of fancy videos like what I just showed you, or a figure like this, that you're just doing it for kind of outreach reasons. No, I mean, people, this is the real data, you know, so people are just experiencing this in the paper and then getting ideas about other things they want to look at and other data they want to add. And then this is published alongside a so-called GLUE session. And so I chose another Orion one. Sorry, this isn't the local bubble but just for Ron, you know, I was like, okay, so here's, you know, super zoomed in karma data on Orion in 3D for 3 different spectral lines. But what I want to show you is this thing is a web of all different data sets that are all loaded in, that are all connected to each other. So the data sets that we used for Catherine's paper here on the local bubble include all the different tracers of dust, of stars' motions, of different molecular line tracers that we wanted to overlay in 2D, and you can just put them all together in this software. Now, of course, you have to have the data, you have to know what you're doing, and you know, this takes a while. It's not yarn, okay? But it's getting toward almost as easy as craft supplies, right? And the thing I haven't told you is that if you go to the actual paper here, I'll just show you here, you can actually go here and download all the data and download the GLUE session file. So I should show you what GLUE is in a minute, but the software that we used, so that you can recreate that paper and you can start from where the paper leaves off with the data. And so pretty much everybody could be doing this right now, and some people are, okay, but almost nobody is teaching how to do this in any kind of educational setting. And so that's what this Cosmic Data Stories project is for, is not to do something quite that complicated, but to try to bring that approach into classrooms. Okay, so now, let's see. I can play with Worldwide Telescope a little. I can show you stuff about augmented reality. I can show you a very short video about what GLUE is, which I keep mentioning, GLUE, GLUE, GLUE. Yes? Okay, we have a lot of votes for GLUE. Okay, so I'm going to show you an old video that we made several years ago, but it was when GLUE could do less, and so it's actually more understandable. So I'm going to show you a video from, like, I don't know, oh, right, I can't do it here. For some reason, if you embed too many times, it doesn't like it. So I forgot that that's broken. I can just go here. So that's the same website, but here it'll work.
People with ADHD save 10
Apparently we have
hours
to watch some
studying
ads
with
first.
this Chrome extension. But no, by all means.
Okay.
GLUE is a
So the
program
voice you're going to hear now is Tom Robitaille, who some of you
for
know.
data exploration and visualization
And he,
that allows
just
users
as an example of a sort of career thing, he's somebody who was an excellent astronomer, made very important contributions to the study of star formation, and then decided that he loved software more than anything else. And so he now is extremely oversubscribed as a software developer. But the 2 people who wrote the original version of this software were Chris Beaumont, who was a graduate student at Harvard at the time, visiting, and Tom Robitaille, who was a postdoc. And let me just tell you that what I wanted was what you're going to see here, where you can, in the logo, which Chris actually also made, it kind of shows you what I wanted, which is if you have a lot of different kinds of graphs, and you want to know, like, oh, this point, what does that point in this graph correspond to in this image or this histogram, et cetera. And so I used to use this software called Data Desk, which is still very good, that uses principles that were put forward by a great hero of Fourier transforms, John Tukey, who was a great statistician who pioneered this thing called exploratory data analysis or exploratory data visualization. And that's really what GLUE is for. That's sort of what a lot of my life is for these days, okay? But it's being able to interact with data in real time and do this kind of exploration, which you can then include or follow up with, you know, super quantitative analysis. But you want to kind of interact real time. So that's what I wanted. But the reason I'm mentioning Chris and Tom is because they were the graduate student and the postdoc. And the first thing they did was not make this possible, but was making the interconnection with between different data sets that had shared attributes possible. Because that's a lot of the grunt work that people either make graduate students do or don't want to do. So, you know, you have a catalog, you have an image from somewhere else, you have a 3D data cube, you have somebody else's image, you have all these things, and they all use different names for the coordinates, or maybe they even have like a different calibration, and you want to be able to interconnect these things. So they made the little hub that interconnects the data sets first. And then the last meaning of glue, so it's not an acronym, so it glues together data sets, it glues together plots, which you'll see here. And then, I don't think it's shown in this video, but it also glues together tools. So whatever software tool you want to use with glue, and by the way, it now runs in Jupyter Notebooks and Jupyter Lab. I'm just going to show you a desktop version. You can plug in, you can make plugins. And so there's a plugin for Worldwide Telescope that we use a lot. So what I think I'll do is I'll show you this video, and then we'll play with Worldwide Telescope a little bit. We'll take some more requests. Okay, so let me just, this is very short.
To better understand the relationships that exist within and between data sets. The main interface of Glue provides different data viewers. In this example, the viewer on the left shows an astronomical image of a region where stars are currently forming, and the two viewers on the right show a scatter plot and histogram derived from a separate catalogue of stars in this region. The viewers support interactive selection of data subsets, and selections are automatically propagated to other data viewers. In this example, the selected stars are shown in red in all viewers. One of the main features of Glue is the ability to link together different data sets using linear or nonlinear mapping functions. In this example, we have linked the image and catalog data to make it possible for the stars to be shown on top of the image. Three-dimensional data viewers are also available. In this example, we can see the 3D distribution of all earthquakes recorded around the world in the last 6 years. The points are colored by the depth of the location where the earthquake originated. The lighter colors show earthquakes that occur deeper in the crust. This viewer also supports highlighting of selections made in other viewers, as well as direct 3D selections. Glue is designed from the ground up to be a multidisciplinary tool and allows users, for example scientists, to develop plugins to support particular data formats or data viewers. This example shows a volume rendering visualization of medical data that consists of braid scans. We have used Glue to overplot two different data sets, and we can interactively explore this data in 3 dimensions. Finally, Glue is written in Python and makes it easy to interact with the data and subsets using a built-in IPython terminal. For example, we can define new subsets programmatically and have these be automatically highlighted in the interface.
So the update to all of this is, like I said, for those of you who like Jupyter and Jupyter Notebooks and Jupyter Lab, this all runs in a Jupyter environment, and a lot
This
of
powerful $99 drone is now available in the US. This is an extremely high
that's happened has been either done at or supported by the James Webb Space Telescope, because Glue was chosen early on. We didn't ask. They just came and Matt Mountain said, could you make this software real? Because we need it for the James Webb Space Telescope. And so if you get JWST data, you're going to get Jupyter Notebooks that use Glue to let you manipulate the data. So have fun. Hang on, let's hide this again. Wow, we got a lot of stuff open here. Sorry, let me just close some of this so we don't go crazy. Sorry. And by the way, while I'm doing all, I could show you this. While I'm doing all this, I just want to thank Jim for this excellent GBT beer opener that is in my pocket. Apparently I closed the actual main page, and it reminded me that actually one of the very first applications, we don't want to edit it though, one of the very first applications of Glue was this project that we did together about Nessie. So Jim's favorite infrared dark cloud, Nessie, which turns out to be much longer than Jim thought. That's what he was talking about. We displayed that all in Glue. So I will now link this beer opener to Nessie. Actually, I have many little models of Nessie on my desk at my office, and I think the beer opener will be worn by Nessie. Anyway, so we were going to play with Worldwide Telescope, but before I do that, I just want to scroll through all this again and ask if there's anything else. This is Worldwide Telescope, which we'll, like I said, play with in a minute. So I showed you Glue, I showed you the path to Newton, I didn't show you anything about uncertainty. Okay, I'll tell you what these...
This cosmic data stories again. Is this where you're talking about doing data science with
Yes.
in high school?
Yes, thank you.
Tell me about that before this is over.
Yes, okay, right. So that is a very new project, and so I will show you here, this is just the website for Cosmic Data Stories at the moment. And what we've done is to get data at a level that we think people can understand. So like for the Hubble one, unfortunately I don't have the live version of it right now to show you, but I can send you a link. So you get, say, all the data that went in Hubble. Oh, I can show you, wait a second. I can show you a live, I can show you something that we had made for the proposal. Hang on, here it is. This again, this is the first thing I did when the pandemic started. I was like, oh, this would be fun. And so I made this plot, which actually turned into this lovely Cosmic Data Stories project from the NASA SciAct. Have you heard of that program? It's their science activation program. So there's groups all over the country that have these relatively big grants to do things in outreach, and especially if they involve NASA data. So let me show you this. So this is Hubble's original plot of velocity versus distance. And so this is, you know, the Hubble relation and the Hubble law. But this is great because it's a segue to worldwide telescope. So what you can do is you could say, okay, well, this is a graph, which might be very boring for students. But like, what are the points on this graph? What does this graph mean? And so if I click on any one of these galaxies, it tells me, oh, this is a galaxy. And then I can click, I just click the button that says, see this image on the sky. And then this is now the web version of Worldwide Telescope, and there's a Hubble image. So it's cute, right? It's the Hubble Space Telescope project about the Hubble law. Okay, so anyway, and it'll show you like what is a high resolution image compared to a low resolution image, and where is this on the sky, et cetera. And so I just got there in, you know, this click, by clicking this, see this on the sky. And so this is just a teeny piece of that Hubble data story, but they learn what spectroscopy is, they have spectra, they get spectra for 4 different galaxies, and they mark the peaks on those, and then their data that they do gets contributed to a data set that's like their whole class or everybody that's ever done the project. And so they learn about, you know, if you get more and more data, how does that improve or not improve your uncertainty? Go back to that in a second. And the idea is that there's some free exploration at the end, and you can make mistakes. And so it has enough technology built in that if they're just messing around, it knows and it yells at them, basically. You know, but if they get 4 galaxies clicked correctly with the spectrum, you know, somewhere in the right place for where the line is, it's like, good, you can go on to the next step. And even if they did a bad job at marking the position of the peak of the spectrum, that still goes in the database, you know, and that's part of what they're supposed to understand. So anyway, we're supposed to do this for 10 different discoveries, and one of them is this Radcliffe wave that I didn't talk about. And so we'll have Catherine, the person you heard narrating, be what NASA calls the SME, the subject matter expert. And so she'll, you know, narrate some introductory videos that'll be for the students, and then they get the data, and they use a version of GLUE, which is less complicated than the version I just showed you. Completely runs in a web page. There's no interface, so they don't know what's, like when they're clicking and they're clicking on galaxies in the sky and then seeing the spectrum for that galaxy, that's GLUE behind the scenes, but they don't know that. But we are going to make a kind of making of thing to explain to the students who are really interested, like, how did we do this? You know, what was the software? Yeah, so is that enough of a quick answer? Okay. And so, yeah, last but not least, before we just play with Worldwide Telescope, this is one of the things that we have, oh, thanks a lot, that we have about uncertainty on the website for the prediction project. And I personally, this is again, I lost all track of time during the pandemic, but apparently must have done stuff, okay? So this is something that we did where, you remember those IHME, the Institute for Health Metrics and Improvement, or Evaluation, sorry, models that Trump was showing on the easel, like very frequently, and like we were all gonna be back in church on Easter in 2020, and I was gonna be here, and it was gonna be great. Yeah, well, so these are those models, and we were trying to explain to people that, you know, here's like before the pandemic, and then these shaded blue regions, let me just zoom in a little bit more, they kept updating the model, okay, because they kept being too optimistic, unfortunately, in most cases. So here's like what actually happened is the red dots, and this is the model that they made at that time. And then, oh, wait, it doesn't seem to work. So we make a new model, and then we'll make a new model, and you'll notice that the models don't overlap especially well. Okay, so in other words, the pandemic should have been over by here, so they had to keep making a new model, and these are supposed to be 95% confidence intervals, and it kept going outside of those way more than 5% of the time. So that was very, very unfortunate. But anyway, there are much simpler things that we offer too, like this one, which is a little game. Oh, it's down here. A game that they can play, that anybody can play. And so we use this with the Harvard students, but we'll probably also use it in the cosmic data stories at some point. And it's just a game using a physics engine where you say, like, I have a puck and I'm trying to slide it at the wall at this cross, but there's some roughness of the table which you can adjust over here, and so it'll deviate more or less from its path depending on how rough you make the table, and then you can talk about trials, and you can have how many pucks and how many games, and it'll build up these distributions, and you can, oops, sorry, I clicked the wrong link. Don't let me do demos. There's some button here, there it is, click here to finish the game, where you can let it just finish for you, and it'll fill them all up, and then you can download the data at the end. And so it's supposed to be kind of scaffolded, where there's like levels of sophistication. Like somebody wants to just understand that you could slide a puck at the wall, and because the table is rough, it's not necessarily going to go where you hit it. And somebody else wants to know, what is the number of trials due to the width of the distribution? And they get really serious about it, and then they download the results, and they get some Excel file, and then they can do whatever they want. So anyway, there's sort of levels of how detailed you can get with these things, but they all rely roughly on very similar technology. So, and this is the weather forecast for Boston with uncertainty. You can play with that later. So my guess is that we should just look at Worldwide Telescope and take some more requests for a minute, and then I'll be done. Does that sound good to you? Yes? Will, would you like to come here as our driver? Okay, so like in Worldwide Telescope here, I could look at the sky, and I could, for example, like pick a different wavelength. Let's pick radio because of where we are. Okay, and I can, unfortunately, radio all sky images are never very interesting. Let me pick one in the infrared. Okay, so let me pick an image of dust on the sky, okay, and I can see the galactic plane, and I can obviously embed this in a website. I can do whatever I want. And I could probably even get this to work. Let's see, if I set something as the background and something else as the foreground, I can slide between them, and I set them both as that was dumb. Sorry. And then I can, mix together different wavelengths, and all of this can happen like at any level where you strip away the interface, and you could do something really simple for children, or you could do something incredibly sophisticated where you see the local bubble or the Radcliffe wave in 3D and mix that into glue, and et cetera, et cetera. But we're tired, so instead what we're going to do is we're going to let you drive around on Mars in 3D. So that's also a Worldwide Telescope thing. So here you go, Will. Will is going to, this is just to show you that it really works, so I'm not going to do it. Oh, you need to take a picture of these people with their 3D glasses like it's the 1950s. Anyway, so I'm sorry again for anybody who's online. We'll just go to worldwidetelescope.org and send me a note, and I'll send you 3D glasses. Does it look 3D to you? Is it pretty good? Okay, tell Will where to go. Forward. He can't because it's only where the rover was. I can move to a different view for the rover.
Suggest following the tire tracks.
Yeah.
Follow the tire tracks.
Go over by that big face.
But you can imagine, right? When you tell a kid, you can do this on the web. Like I'm running this in Windows so that we can use the Xbox controller. But if you're going to use a mouse, or if you have a magic controller that can work with the web, there you go. This is pretty great. And so the whole Worldwide Telescope Ambassadors program that I mentioned that the Cosmic Data Stories thing came from was because Steve Strom, who some of you know, saw a demo of Worldwide Telescope that we were giving in like 2009. And he yelled at me. And he was like, why don't you have an educational program based on this? And you should have a STEM. Anyway, and so we made the Worldwide Telescope Ambassadors, and there's a wonderful woman whose name is Pat Udon-Persert, who you should know, Suzanne. And she, by the way, hates the Xbox controller. See, I'm not gonna let you play with that. So if Pat ever sees the recording of this, she'll go, see, don't give anybody an Xbox controller. Anyway, she runs the whole project and she's in charge of the cosmic data storage also. But she hates the controller.
Is this some kind of manipulation of the data, or is this a stereo camera?
That is a darn good question. I believe they had stereo cameras on the rovers. They did. Okay, Jim said yes.
That's so cool.
Yeah, there's a whole lot of 3D imagery, including of cosmology level, galaxy catalogs in Worldwide Telescope. But I think the Mars ones are the most fun. There's also the Moon, and there's plenty of other places on Earth. By the way, you can also put your own stereoscopic images into Worldwide Telescope if you want. And what I want to see, Will, can I switch for a minute to here? So why don't you take a look at the Earth? I don't know what will happen with the Xbox controller here. Does that do anything interesting? So yeah, and you probably could zoom way in, see if that works. Yeah. So anyway, so here's the Earth, and so you can put any image on the surface of a sphere in Worldwide Telescope, and so that's what I meant, Jim, when I said I want to see that radar image.
Yeah,
The sphere.
Oh.
I think I can turn the clouds off. Would you like me to turn the clouds off? I think.
That's why we operate.
Oh, that one still has clouds? Huh. I can give you Earth at night. I think the clouds are live. Hang on, let me see if I can turn that off. Settings. Right, wouldn't it be great if you could do that in real life? Advanced. No, oh, I know where it is. It's in the layers. Sun, Earth, where are we? I didn't plan to do this. Does anybody see something that says clouds? Oh. People will be so disappointed. Oh, Earth, expand, overlay, cloud layer. There you go. Magic. Okay.
We have the labels back on.
Oh, you want the labels? Yeah. By the way, when you give this to sixth graders, this is the first thing they do. Always find their house.
Find where they live.
Will is playing the part of our sixth grader today. Oh, so that's where Monterey is. I drove through there.
Durban.
Oh, wait. Did I tell you that also you can tilt it? Very good, Will. Very good. Sometimes, hang on. Oh, look at that. Look at that. Sometimes, let me try this. You can, which one is, oops, that's the wrong key. It's this one, yeah. So I can tilt it. And they don't, they have some kind of, they have some sort of elevation model, and it's not exactly perfect, is it? Yeah. Well, look at what happened to the GPT. I'm so sorry. All right, here, wait. Let's just let Will fly around in the 3D solar system here for a minute. Let me turn off all the constellations. I don't think we want that. Okay, well, here, go ahead. You want me to? Oh, let's turn on some nice orbits. You want the International Space Station on? Oh, it's much more fun if I turn on all the asteroids and maybe some orbits. Oh, you want me to turn on time too? So here's time going 10,000 times real time. So now I can make them all move. If you zoom out a little bit, people can see. So those are from the Minor Planet Center. So those are real. This isn't some kind of animation. This is actually the things that we know about. And now you see that they don't look like they're moving because they have to turn time up even farther here because we've gone farther out in the solar system. So yeah, this program, we started working on this, and really this was the brainchild of Curtis Wong at Microsoft Research. And then there was a genius developer who worked with Curtis named Jonathan Fay, and I was just the pet scientist. I was like, oh, it'd be nice if we could do blank. I knew we'd do it. But it's amazing to me that it started in 2008. but the web versions, and there's something called PyWWT again, for those who like Python, that is a plugin for anything, so not just Glue, but anything that runs Python. And so there's actually some serious interest and use of Worldwide Telescope displaying archival data from observatories and also public outreach, but a lot of more research use these days. Well, you want me to just turn this time down now so you don't get nauseous? Here you go. Is that better? If somebody else wants to play around, that's fine, but this seems like enough, Jill, right? Would you just keep playing? Okay. We'll say I'm done, and you can look at the website for. I hope you don't mind that I didn't give like a straight up lecture. I just thought it would be more fun to play. And remember, the point is, it's fun, right? Like you get to discover stuff, you get to help people learn things, and you do all this. And I've had a lot of people helping me, so don't get the idea that I did this on my own. So I'm very, very grateful to the probably 300 people I cannot mention who made all of that possible. So thanks. So we're not done with our evening, because you can now play with that, and we have, Will, do you have the Ethernet connection for a phone? If anybody wants to play with the augmented reality, then you get to do that too.
Jill, do we have any questions from our virtual?
Ah, yes.
Just asked
Sorry.
if we have any questions, and I haven't had any come in yet.
I'll just let this play silently in the background so you can see how this works. Let me turn the sound down. Okay, so this is that little green shell that you saw off on the side of the local bubble. So this paper came out first, and there's an interactive figure in the paper. By the way, from Glue, for those of you who know what Plotly is, there's a button where you just export to Plotly from Glue, and then you can just publish the figures immediately. Although I was talking with my collaborator the other day, Sylvain Corlet, who does a lot of work on Jupiter. So we have a collaboration directly with Jupiter now, between Glue and Jupiter, funded by the Moore Foundation. And there's a version of Jupiter called Jupiter Lite now that runs in a web page with no kernel. Like, for those of you who know what that means. And so it means that you can have papers that essentially are Jupyter notebooks, so even beyond what you see here, where like the entire paper is just some interactive session with a lot of text in it. But it's not something that anybody has to be running any kind of software. It's just running completely in the browser. It's amazing. So anyway, you just scan these codes, and I will leave this open so that you can scan the codes and try it. But you can only try it with a phone that's connected to the internet. So there will be one somewhere. Where do you want to put it?
Oh, that's what you were doing right now. I'm sorry, I misunderstood.
We'll do it up front. It'll take a minute.
Okay, no problem. So anyway, and you can see, right, I promised to tell you what all the software and people were in one of these videos. And so here's just an example from a different video of like, that's the software stack, okay, to do what you saw. But most of it is completely hidden from the user.
And so there are examples now of online papers, like if you go to a journal.
Yep.
And you find the figure in the journal article.
Yep.
And you can twist that figure around.
Oh yeah, exactly. So I will do that right now. So we'll just pick one. Let's pick the Radcliffe wave. Or, well, I showed you this one already. I'll show you Radcliffe wave. Okay, so here's like the website that we made to explain the Radcliffe wave. Let me turn this thing off again. Okay, and the figure is in the paper, so let me go pretend that I didn't already have the paper on my computer. So I'll click this, and I'll open the actual paper, and here it says, here's this figure, and I'd like to interact with that figure, so I click here, and then here's the figure, you know, and it's like, oh, actually they didn't show me the model for the Radcliffe wave. I'd like to see that. I don't care about these other clouds, et cetera, et cetera. Oh, I just want to see it from the side. I want to see it from the end. So yeah, that's just in the...
That's Plotly at this point?
This is Plotly.